Hello, welcome to another module in this massive open online course on estimation for wireless communication. In the previous modules we have looked at equalization to overcome the inter-symbol interference of a wireless channel, and today we are going to look at a very different technology, a very modern technology in fact, to overcome the same problem, that is inter-symbol interference in a wireless channel very efficiently, and this technology is OFDM or orthogonal frequency division multiplexing. So, from in today's module we will start looking at OFDM. So, we are going to start looking at estimation specifically for OFDM, that is our aim starting this module, that is estimation for OFDM, where OFDM is an abbreviation, it stands for orthogonal frequency where OFDM stands for orthogonal frequency division multiplexing, and in fact OFDM is a very modern technology and OFDM is a very important technology. As you might all be familiar, OFDM is used in the 4G wireless cellular standards such as LTE, WiMAX, and it is also used in the modern wireless Wi-Fi standards such as 802.11n, 802.11ac and so on. So, OFDM, this is a very modern wireless technology, or one can say it is the latest wireless technology, and this is used in 4G standards such as the 4th generation cellular standard, such as for example, it is used in your LTE, which stands for long term evolution. It's used in the WiMAX standard and is also used in other standards such as Wi-Fi, for instance 802.11n, 802.11ac and so on. So, OFDM is a very powerful and a very important technology because its wide applicability in the modern 4G wireless standards as well as the Wi-Fi standard. So, to understand estimation for OFDM, we have to first understand what OFDM is about, or what orthogonal frequency division multiplexing is about. So, to understand that, let us again start with our ISI, or inter-symbol interference limited channel, and as we already seen many times before, we have described it previously. The ISI channel has been described, as your Yk, that is received symbol at time k equals H0 xk plus H1 xk minus 1 plus Vk, that is Yk, this is the received symbol at time k, xk is transmitted symbol at k, this is the transmitted, xk is the transmitted symbol at time k, and xk minus 1 is the previous symbol, this is the transmitted symbol at time k minus 1. Therefore, what we have is that the transmitted symbol at time k minus 1, which is xk minus 1 is interfering with xk, which is the transmitted symbol at time k, and this is what we term as inter-symbol interference. Alright. So, what we said is basically inter-symbol interference is caused by the fact that xk minus 1, which is the transmitted symbol at time k, minus 1 is interfering with xk, which is the present symbol. So, the past symbol is interfering with the present symbol, this is inter-symbol interference. So, this is the model for your inter-symbol, this is the model for your ISI channel, where ISI stands for, and this is also something that we have seen before, where ISI stands for inter-symbol, where ISI stands for inter-symbol interference. Okay. And previously we have seen that OFDM is a technology, previously we have seen that equalization is a technology to overcome inter-symbol interference, alright. And now what we are saying is that OFDM is another technology which can overcome this inter-symbol interference and very efficiently, right. So, we are going to see that. So, previously we have seen equalization overcomes ISI, and OFDM is another technology to overcome ISI even more efficiently meaning lower computational complexity, so that it is easier to implement. OFDM overcomes ISI. OFDM has many advantages. One is that it overcomes ISI with very low complexity, and that is the advantage of OFDM, or orthogonal frequency division multiplexing, that it is a very low complexity or a very efficient scheme to overcome the inter-symbol interference in the wireless channel. Okay. So, this is a very low complexity. OFDM is a very efficient scheme. OFDM is a very efficient scheme, and that is what has made OFDM such a cutting edge wireless technology for employment in the various 4G wireless standards such as LTE, WiMAX, and also the Wi-Fi standards that we have talked about. And now what we are going to do, we are going to first, I am going to describe the model, the system model, that is how to describe how this OFDM based wireless communication works, and then we are going to look at how to perform estimation in the context of an OFDM system. Alright. So, first we are going to look at what is this OFDM, or what is an OFDM, that is how does it work, that is what is the transmission scheme for OFDM, and that can be explained as follows. So, OFDM can be explained as follows. So, consider the following symbols. So, consider the following symbols to be transmitted in the OFDM symbol. Let us say we have 4 symbols which are going to denote by x0, x1, x2, x3. So, these are the 4 symbols which are to be transmitted. So, we have capital N equal to 4 symbols, and this is also termed as the number of subcarriers, capital N equal to 4 capital N equal to 4 subcarriers. So, we are looking at, so this capital N is an important parameter in this OFDM system. We are saying we are going to use capital N equal to 4 symbols. These are denoted by x0, capital X0, capital X1, capital X2, capital X3. It is important to note that we are representing them by capital X, because we will use small x to represent something else. So, we have N equal to 4, capital N equal to 4 symbols, correct, and also this is known as capital N equal to 4 subcarriers. We say that these symbols are loaded onto the capital N subcarriers, that is the capital N symbols, that is the N symbols are loaded into the onto the N subcarriers, that is capital X0 is loaded onto subcarrier 0, capital X1 is loaded onto subcarrier 1, and so on, capital X4 is loaded onto subcarrier 4. So, this, let us clarify this also, capital XL is loaded, the terminology used is loaded onto the lth this is loaded onto the lth subcarrier. There are 4 symbols, they are loaded onto the 4 subcarriers, alright. And so, in a general scenario, you have capital N symbols and they are loaded onto the capital N subcarriers. Now, what does it mean to say they are loaded onto the subcarriers, and this is what it means to say they are loaded onto the subcarriers. So, we have the symbols X0, X1, X2, X3. Now, to these symbols, what we do is basically, what we are going to do with this symbol, these symbols are, we are going to perform the endpoint IDFT, that is endpoint IDFT, which is IDFT stands for, as you all are should be familiar with, this stands for the inverse discrete Fourier. IDFT stands for the inverse discrete Fourier transform. To get the IDFT samples X0, X1, X2, these are the small x's, small x0, small x1, small x2, small x3. So, n equal to n point IDFT, or in this case basically you have n equal to 4 point IDFT. So, you take the symbols which are the capital X0, capital X1, capital X2, capital X3, yeah, alright, and you load them onto the subcarriers, which means basically you take the n point IDFT, that is the inverse discrete Fourier transform. This can also be performed very efficiently, very fast, in a very fast manner using the inverse fast Fourier transform. So, typically you will also see basically it is the n point IDFT, which is the same as the n point IFFT. IFFT is simply a fast algorithm to perform the discrete Fourier transform, inverse fast this performs the inverse fast Fourier transform. Therefore, now what you have is you have capital X, that is the X of k is the sample, is basically corresponds to the inverse fast Fourier transform. As you know, this is given as 1 over n summation L equal to 0 to n minus 1 capital X L e to the power of j 2 pi k L divided by n. This is the expression for the IDFT. All of you should be very familiar with this, which is basically now setting n equal to 4. For n equal to 4, this is basically given as xk equals 1 over 4 summation L equal to 0 to n minus 1, which is equal to 3 x to the raise x L e raised to j 2 pi k L divided by n, which is 4, which is equal to 1 over 4 for this specific example. Please note that this is only for this specific example corresponding to n equal to 4 subcarriers, L equal to 0 to 3 x L e raised to j pi by 2 k L. All right. So, this is the expression for the, remember x k is the kth sample. So, small x k denotes the sample, capital X L denote the symbol loaded onto the Lth subcarrier, small x k is the kth sample, which is generated by the kth IFFT point of the capital X's, capital X 0, capital X 1 up to capital X n minus 1. Okay. And now these samples are transmitted over the channel subsequently, but before transmission over the channel there is another important operation to be performed, and that is as follows. So, we have the samples x0, x1, x2, x3, and what we are going to do now is basically we are going to take the last sample x3 and again place it before x0. So, we are doing a prefix. So, what are we essentially doing is we are prefixing the samples. So, these are your samples, and what is this? This is your, this is a very important thing. We are doing a prefix and we are cycling the samples from the end towards the beginning. So, this is termed as a cyclic, and this is a very important concept in OFDM. This is termed as the cyclic prefix, simply denoted by the term CP. So, what we are doing is basically we have these samples small x0, small x1, small x2, small x3. Now, we are prefixing this by taking x3 from the back, that is we are copying x3 from the tail of the block and repeating it again at the head, that is we are prefixing the block with x3. Alright, so, it is a prefix, and since we are cycling the sample from the end of the block towards the beginning, this is known as a cyclic prefix. So, we are simply copying some samples from the tail of the block and prefixing them at the head of the block. This mechanism or this step in OFDM transmission is known as a cyclic prefix, the addition of the cyclic prefix. So, first you take the symbols which are loaded into the subcarriers, perform the IFFT. After the IFFT, you add the cyclic prefix. Following the cyclic prefix, the samples are transmitted over the channel. So, now after addition of the cyclic prefix, so we have the samples x0, x1, x2. So, this is your block after addition this is your block after addition of the cyclic prefix, and this is then transmitted over the after the addition of the cyclic prefix, this is transmitted over the channel. And remember, our channel is basically the intersymbol interference channel, where yk equals h0 times xk plus h1 times xk minus 1 plus Vk. This is our channel. Now, if you look at the symbol y0, we have y0 equals h0 x0 plus h1 times the previous symbol, but the previous symbol you can see is x3 because of the addition of the cyclic prefix. X3 becomes previous symbol of x0. So, this is the previous symbol of x0. So, this is h1 into x0 plus v0, and that is, I am sorry, h1 into x3 plus v0, because x3, because of the addition of the cyclic prefix, where x3 has been moved, that is copied from the tail of the block and prefixed at the head of the block because of the cyclic nature of the prefix, x3 also is the previous symbol to x0. Therefore, you have y0 equals h0 x0 plus h1 times the previous symbol, which is x3 plus v0. And of course, now for the rest of the symbols we can write it as usual, that is y1 equals h0 x1 plus h1 x0, which is the previous symbol of x1 plus v1, y2 equals h0 x2 plus h1 x1 plus v2, y3 equals h0 x3 plus h1 x2, which is the previous symbol to x3 plus v3, and this now gives us, this now basically gives us the received symbols across the, so y0, these are the received symbols. These are the received symbols across the, these are the received symbols across the channel. All right. So, we have the small y0, small y1, small y2, small y3, which are the received symbols. Now, let us observe an important property of the small y0, small y1, small y2, small y3, which are the n received symbols. Now, what I am going to do is I am going to illustrate with a figure, because with a figure it is best illustrated pictorially with the aid of a figure. So, let us use, I think let us have here, what I am going to draw is the time axis with x0, let me draw it clearly. I have x0, x1, x2, x3, and let us say this is your x0, let us say this is your x1, this is your x2, and this is your x3. Now, look at this, at time k equal to 0, that is for yk, at time k equal to 0, what do we have? At time k equal to 0, if you can look at the expression above, you have h0 times x0 plus h1 times x3. So, I can write it as h0 times x0 plus h1 times x3 plus 0 times x1 plus 0 times x2. So, what I get is h0 times x0 plus h1 times x3, that is the effect of the channel on the symbols. Now, let us look at time, let us again now look at time k equal to 1. At time k equal to 1, I have h0 times x1 plus h1 times x0. So, this is h0 times x1 plus h1 times x0 plus 0 times x2 plus 0 times x3. I can also include x2, x3 by simply putting zeros, correct. And at time k equal to 2, now look at something interesting. At time k equal to 2, I have h0 times x2 plus h1 times x1. So, h0 times x2 plus h1 times x1, and now if you can see at time k equal to 3, I have h0 times x3 plus h1 times x2 plus 0 times x1 plus 0 times x0. And now, as you can see, as a result of this, and if you observe closely this figure, what you can see is basically I have the symbols x0, x1, x2, x3, and I have the channel taps h0 or the channel filter h0, h1, and you can see is that the channel filter is rotating over the transmitted symbol. So, you can see in the first step we have h0, h1, in the next step h1 has circularly shifted to the left. So, h1 has circularly shifted. So, if you can observe this, this is basically a circular shift. h1 has circularly shifted to the left, h0 has moved to the right. In the next step both h1 and h0 have moved to the right, and then in the next step h1 and h0 have moved to the. So, this is basically a circular shift of the filter, channel filter over the symbols x0 and x1. So, if you look at this, what this represents is something very important, that is a circular shift of channel filter, or basically your channel taps or basically channel filter over the samples x0, x1, x2, x3, and therefore, the important point that it is a circular convolution, it represents a circular convolution. So, the output y equals h circularly convolved with x plus, of course, there is the noise with v. So, this represents your circular convolution. So, what we have is, if you can look at this, is basically the action, because of the addition of the cyclic prefix, the action of the channel filter on the input symbols is such that basically at every point in time you are rotating the, that is you are circularly shifting basically the channel filter, right. So, h0 is first to the left, h1 is to the right, and the next step h1 has circularly shifted to the left, h0 has shifted to the right, and then they are shifting, then with every time instant they are shifting one step to the right, and of course, towards when they reach the end circularly shifts back to the beginning, and that is basically the very definition of a circular convolution. Therefore, the action, because of the addition of the cyclic prefix, the action of the channel on the input symbols is such that it represents a circular convolution, and therefore, the output y is basically the circular convolution of the channel filter h with the samples x plus the noise, and this is the important point. What is this? This is the circular convolution. By addition of cyclic prefix, we have converted the output of a channel into a circular convolution. So, addition of, and this is also important to realize, why is this why is the circular convolution arising? Addition of cyclic prefix has converted the linear channel or linear convolution has converted a linear convolution, and otherwise linear convolution, to a circular convolution, and that is the important part. And therefore, now we know from the properties of the circular convolution, that is, if you take the FFT of h and x, that is circular convol, then the FFT, in the FFT domain, it is simply the product of the FFTs of h and x. So, what we have is, because we have circular convolution, if we take the FFT of y, that is equal to FFT of h circularly convolved with x plus v, which is the noise. Now, the FFT operator is linear. So, that is simply the FFT of h circularly convolved with h plus the FFT of v, which is now, if you look at this, the FFT of a circular convolution is the product of the FFT. So, this is basically your FFT or H times the product. Remember, the circular convolution in the FFT domain becomes the product plus the FFT of V, and this is a very important. So, this circular convolution has now been converted into circular convolution becomes product in the FFT domain, or basically your frequency domain. Alright. So, basically that is the addition, that is the interesting aspect of OFDM, where we have taken a block of symbols, the capital X's, capital X0, capital X1, capital X2, capital X3, performed the IFFT, or the IDFT to generate the samples. To the samples we have added the cyclic prefix, and now once you look at the output of the intersymbol interference channel, you see that basically what the channel is performing is equivalent to a circular convolution. Therefore, if you take the FFT at the receiver, in the FFT domain the channel is basically the product. So, FFT of Y is basically equal to the FFT of the channel filter H times the FFT of the samples, that is the small x, plus of course the FFT of the noise, that is V. Alright, and this is the important, this is the key equation in the OFDM which describes the OFDM system model. So, with this model we will stop here, and we will continue to explore this aspect and the implications of this aspect in the next module. Alright, thank you, thanks very much.